So in the last video, I went over a little bit about the matrices used in Dirac notation. And we talked about, like I said, what was called the Hermitian Matrix. Um, and so the Hermitian Matrix, as I said in the last video, was one where if you take the transpose of it, uh, then you end up with some. Well, I'll state it this way. If you take the transpose and the complex conjugate, which we denote as H dagger, if it's Hermitian, then you end up just getting the matrix back again. And so that was sort of the main thrust of the previous video, and we called these, as I said, Hermitian matrices. In this video, I want to talk a little bit about bases. So the basis vectors, the plural of that is bases, and components of vectors, and sort of how we handle those using our Dirac notation. So I have here sort of this enlarged looking set of basis vectors, and so we will say that each one of these is one in magnitude, and so the direction of them are sort of orthogonal to each other. Each of them are perpendicular to each other. And so the way we can represent this using vectors is we have our E1, which I have right here, and we will say that that is 1, 0, 0. Then we can have our E2, or E2, which we will have as 0, 1, 0, like that. And then we could have our E3 as 0, 0, 1. And so this is telling us that we are going 1 in this direction, and then 0. There is 0 amount of it going in this direction or in this direction. And sort of the same with the other ones. This says that we have 1 going in this direction, but there is none of it that goes in the E1 direction or the E3 direction, and E3 is all in this direction, and none of it is in the E1 or E2 direction. And so we call these orthonormal, so orthonormal bases. And so there are a couple important properties when it is ortho and normal bases. And so the orthogonal means that if we take the inner product of any two of them, so if we have, say, E1 here, and we take the inner product of it with E2, that we end up with 0. But if we take the inner product of E1 with E1, then we end up with 1. And so we can generalize this and say that if we have EJ, EI, it equals 1 if I equals J, and equals 0 if I is not equal to J. And so that means that we have an orthogonal basis. Well, up here, this means that we have a normal basis, and down here means we have orthogonal. Well, I guess I should be a little bit clearer on this normal. So normal means that if we have any vectors like this, that it will equal to 1. And so that essentially means that all of the components of these are less than or equal to 1. And so that is how we have our orthonormal bases. And so when we have a vector like our uppercase A here, we can, if we can write that as a ket vector here, and we can say that that it is equal to some component times our E1 basis plus some component times our E2 basis. These two components being different plus some other component times our E3 basis. And this is for a three-dimensional vector. We could have this go on to an times en if we want to go to higher dimensions, but I like to keep it simple and just keep things in either 2 or 3 dimensions. And so this is the components and the bases for our vector, which is the uppercase A here. And so we can simplify this down to saying that it is equal to the sum over I of alpha I E I here. And so this is often one of the ways that you won't see that written like this with this summation rather than just writing it out like this, which can take up more time. And so I talked about up here we had this bra vector here for with the EJ, and so the same applies as before, where if we have if that the bra, which I'll write as EJ, is equal to EI, but complex conjugated, and so if our E1, as we had up above, was equal to 1, 0, 0, then our EJ, I'll keep, well, I think I had this more concrete here, so we'll call this E1 as a bra vector. We can say that that is 1, 0, 0. And then if we think about it like this, we can see how our orthonormal bases work, where if we have 1, 0, 0 multiplied by 1, 0, 0, then we have 1 times 1 here, which is 1, plus 0 times 0, 0 plus 0 times 0, 0, and so that equals 1. However, if we have, say, for instance, 0, 1, 0 times 1, 0, 0, then it's 0 times 1 is 0, 1 times 0 is 0, and 0 times 0 is 0. And so that equals 0. And so we need our bases to have the components here in the same position, so that we can end up with the 1, whereas if they're in different positions we end up with 0. And as I said, that was sort of our definition up here of orthonormal bases, where if j and I are equal to each other, then it's 1, and if they are not equal to each other, then it is 0. And so sort of moving on here, like I said, we can say that that EI is well, if we complex conjugate that, then we say that that is equal to EJ here. And so what we can do is we can say that if we have our ket here, we can say that that is equal to the sum over I of alpha I E I, like this. Then we can actually multiply both sides by the bra vector, which is EJ, and then what we end up with is EJ inner product with our ket A there, and then that is equal to the sum over I of alpha and then we've multiplied this side by that ej as well, and so we have ej ei, and we know, as we said before, that this is equal to 1 if I equals j and equal to 0 if I does not equal j. And so what we can say then is that well, this is essentially the identity matrix here. And then so what we can say is that if we have Ej times our ket A, the inner product of these bases with our ket A, since, like I said, this is essentially the identity matrix, then all we have here is our alpha. And so these are the vector components here, vector components, which is like we showed up here, where these are the vector components, these alphas. And so what we can say here is that the vector components, that the alpha I, the vector components, are equal to the inner product of our vector with the basis vectors. And so we take the inner product of our vector with the basis vectors, and that's what gives us the vector components. And so that's pretty much similar to what I showed before, because if we have if we have this, then what we are doing is essentially Ej times A1, or we'll call that A1. That's our first component. Well, I think I had that written up here like this, so we will just say that this is yeah, so we'll just call this alpha 1 plus Ej alpha 2 plus Ej alpha 3, and these j's should actually be 1, 2, and 3. And these, as you see, are in bra notation here, which means they are the complex conjugate. But since we are not using complex numbers here, then they are just the same as the ket vector. And so we just end up once again with our alpha 1 times E1 plus alpha 2 times E2 plus alpha 3 times E3. And so we just end up with what we had up here. And so that's taking the inner product of the vector with the basis vectors. And so what else we can do here is since A is equal to the alpha, well, the sum over I of alpha I times E I, then we know that E J inner product with our vector A is equal to alpha I. Then we can say that that our vector A is equal to the sum over I of, I can draw that a little better, of E J A times the ket version of E here. And then what we can do with this is just sort of shuffling these around. We end up with our ket vector here, I, and then we have our EJ times our EI, and that times our vector here A. And so we said before that this is the identity matrix, and that tells us sort of what this is, where we have instead of doing this, we are instead doing, so we call this the inner product. We are instead doing this, which you may have guessed is called the outer product. So this is the inner product, and this is the outer product. And so the inner product gave us a scalar. So this gave us a scalar when we took the inner product, which as I said, when we're taking the inner product of our basis vectors, if I equals j, then the scalar that we get is 1. If I does not equal j, then the scalar that we get is 0. But if we take the outer product, then what we actually get is a matrix. And so what we can do is we can take our ket, and we can say that we have maybe E1, E2, E3. So ket is our column vector here. Then we multiply it by our row vector here, which is E1, E2, E3. And remember that this should also be complex conjugated, but since we're only using real numbers, we can just do it like this. And so what we end up getting, so we just fill out a matrix, and we start with E1, E1. So we end up with E11, we'll call it there. Then we go to E1, E2, so we have E1, 2, then E1, E3, E1, 3. Then we just move down E2, E1, E2, 1, E2, 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 2, E2, E3 is E2, 3, and then we just keep going like this, just filling these out, E3, 3. And so this is the outer product using the bases, which, as we know, are only 1 when these two are equal to each other, so we will end up with 1s down here, and everything else will be 0, which, as I said, was our identity matrix. So that's 1, 0, 0, 0, 1, 0, 0, 0, 1. And so that we ended up with our identity matrix when we did it with our basis vectors here. But it's you can take outer products with components as well. So if we had, say, alpha, we had our alpha I, and we took the outer product with our alpha j here, then we end up with a matrix that has the I and j, which, as we know, will be something that looks sort of like this: alpha 1, 1, alpha 1, 2, alpha 1, 3, alpha 2, 1, alpha 2, 2, alpha 2, 3, alpha 3, 1, alpha 3, 2, alpha 3, 3. And so that is our outer product with the components here. Yeah, and so that is everything I think I wanted to talk about in this video. So just to refresh, we first talked about our orthonormal bases, which, as I said, are if we take the inner product of the bases, if they are orthonormal, then we will get 1 if I equals j, and we will get 0 if I does not equal j. And we saw here that we can get our components of the vector by taking the inner product of the vector with the basis vectors. So, yeah, inner product of vector with the basis vectors is our vector components. And then we talked about the outer product here, which instead of giving us a scalar the way that the inner product does, it gave us a matrix. And so those are sort of the take-home messages: was the orthonormal bases, the inner product of the vector with the basis vectors giving us the components, and the outer product two of a well between a bra and a ket gives us a matrix. And if it's with the orthonormal bases, then it will give us the identity matrix. And so I hope that this video was enlightening to you, and I will see you in another video.